Hello everyone. So I've been noticing a couple comments in our forum just about understanding the end behavior of polynomials and understanding what's going on with these horizontal asymptotes when we're looking at rational functions. So a lot of this has to do, I'm going to move the camera a little bit. Whenever we're thinking about horizontal asymptotes, we're oftentimes thinking about end behavior. I want to know what's going on with these functions as x is getting really, really large, or as x is getting really, really, really small. By small, I mean getting towards negative infinity. Now, an argument that I was making is when we're looking at a polynomial, what we want to know is what's happening to the polynomial as our inputs get really large. Or say, well, I could say, well, what I argued is that as x gets really, really large, this function, p of x, even though it has, 4 terms in it, it's really pretty much going to be the same thing as 4x cubed. And the reason, this is only as x gets really, really large. I'll also argue it's going to be the same thing as x gets towards negative infinity. I'll show you with this table, but the idea here is x cubed, when I cube a number, it grows way faster than an x squared or an x, adding 7. So check out this table I've made. So we're going to specifically look at each of these terms separately, and then we're going to think about summing them all together. Notice for small x, if x is 10, well, when I plug 10 into this piece, I get 4,000. If I plug 10 into this piece, I only get negative 200, then 30 and 7. Notice that this 4,000 is, quite a bit bigger than these. And even if we sum them all together, you notice that the input, adding them all together, the output of this function, when we plug in 10, is not too far away from me just looking at evaluating the leading term. Similarly, look for x equals 100. This is 4 million for the 4x cubed piece, 4 times 10 to the 6 in scientific notation. Well, if I plug that into negative 2x squared, that's negative 20,000, or negative 2 times 10 to the 4th. I mean, this is quite a bit bigger than this piece. And notice that this is almost kind of like, this is trying to take away from this. This is trying to take away, but it's not really strong enough. X squared isn't really strong enough to affect how strong x cubed is. I mean, look at all these pieces, and when you add them all together, this is trying to lower this value, but it doesn't lower it by too much. The output for this function and the output for just its leading term, they're pretty much the same. Now, this gets even more clear as you plug in larger outputs. Look what happens when I plug in like 10,000. I'm not even like plugging in 1,000,000. I don't even have to really, saying as x goes to infinity. I mean, infinity really isn't that far. I don't really have to go that far out relatively to see that this is happening. Look, when I just the 4x cubed piece, I get 4 times 10 to the 12. That's a 4 with 12 zeros on it. Now, if I just take into account all these pieces here, even though this piece is pretty large, a negative 2 times 10 to the 8, when I add these all together, you just get 3.999 times 10 to 12. These are pretty much the same number. So as x is getting really, really large, this polynomial, it's pretty much behaving exactly like 4x cubed. Their outputs aren't too much different. Now, this isn't just true when we go to infinity. It's also true if we go to the other direction, if we go towards negative infinity. Here I'm plugging in negative 10,000. If you plug in negative 10,000, for this piece you get a negative 4 times 10 to the 12. Here are all the other pieces. But if you add them all up, evaluating this function versus just evaluating 4x cubed, look, their outputs are pretty much the same. So for polynomials, for any polynomial, when you're thinking about the end behavior, you only really have to focus on the leading term. I just think about the end behavior of the leading term. Well, this is a 4x cubed, and x cubed looks like this type of action. So, let's see, backwards. Looks like this type of action. This is positive. So, as you're getting really, really, really big, it should be getting really big. Look, it's getting really big. And, as I'm going towards infinity, the output should be going towards infinity. And as we're going towards negative infinity, we're getting towards negative infinity. It's behaving just like the end behavior of a cubic. So whenever we're looking at polynomials and I want to know the end behavior, the leading term is going to be so much more powerful than all the other terms. So the end behavior of a polynomial will always be the end behavior of the leading term. Okay, so now let's go ahead and talk about horizontal asymptotes. Okay, so when we're talking about the horizontal asymptote, now these are properties of rational functions. Okay, so let's say we have, I don't know, something like 3x cubed, we could even, how about, 4x cubed plus a 2x squared minus a 5x plus a 7. Let's say this is all divided by a I don't know, how about a 2x cubed minus 3x squared plus 9x minus 12. This is a rational function. And what I would like to know is what is going on with this function as x gets really, 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 really large. I'll give you two different arguments. Okay, since I have a polynomial in the numerator and the polynomial denominator, okay, well, our big question is what's happening as x goes towards infinity? Or even as x goes towards negative infinity? What's this function doing as my outputs get really big? What's this function doing as my outputs get really, really negative? Well, as x gets really big towards positive infinity, or when x gets towards negative infinity, I'm making kind of a loose argument here. Well, this polynomial in the numerator will behave pretty much the same as 4x cubed. So this numerator, just as x gets really large, is going to be approximately 4x cubed. The denominator here, well, the 2x cubed is going to dominate. As x gets really big, or as x goes towards negative infinity, this 2x cubed is really going to dominate all the other pieces. So this polynomial will approximately be 2x cubed. So as x is getting really large, the numerator is behaving a lot like 4x cubed, and the denominator is behaving a lot like 2x cubed. So now this is only true as x gets towards infinity or as x goes towards negative infinity. You can loosely think that these x cubes cancel each other out, and 4 divided by 2 is 2. So all I'm saying is that as x is going towards infinity, I'm saying that r of x is getting closer to 2. I'm also saying as x goes towards negative infinity, r of x is going towards 2 also. This is the end behavior. The function is eventually going to settle on this horizontal asymptote, y equals 2. Now, there was another great question in the comments about why is there only one? Why is there only one horizontal asymptote? Well, the main idea here is horizontal asymptotes have to do with the end behavior of a polynomial. As they're getting really large from either direction, it's settling on one location. It has to do with the end behavior. The horizontal asymptotes have to do where the function is settling. It's only going to be able to settle on one spot. If it had multiple horizontal asymptotes, there would have to be 2 locations that it would be settling on. Maybe it's settling on 3. Is it settling on is it settling on 2? If it had, is it settling on 5? Well, if it had 2 horizontal asymptotes, it would, which one's it going to settle on? It has to settle just on one of them. So that's why there's actually only ever going to be one horizontal asymptote for our rational functions. Okay, so that's why in the situation where we can think that if the numerator and denominator are tied in the war, the horizontal asymptote is going to be the ratio of their leading coefficients. Okay, if I change this a little bit, maybe the denominator is winning the war. Maybe the denominator is winning the war. So maybe I put a 4th here. Well, as x gets really large, the numerator will be like roughly a 4x cubed, and the denominator will be more like a 2x to the 4th. You can think loosely that this x cubed will cancel with 3 of the x's, and this will just end up being what? 2 over x. 2 over x. But as x is getting really, really, really large, well, 2 over x, this is getting closer to 0. So when the denominator is winning the war, the denominator is getting a lot larger than the numerator. If I have a really large denominator and a really small numerator, I'm getting closer to, I mean, it's pretty much zero. I like to, always think about everything in terms of pizza. If you take a pizza and you cut it into 10 slices and you took 2 of those, well, you got a fifth of that pizza. Sweet. But if you took that pizza and you cut it into 1,000 pieces and you just took 2 of them, you don't really got that much pizza. If you took a pizza and you cut it into 1,000,000 slices and you took 2 of them, you might as well just have no pizza. You're pretty much approaching zero. So if the denominator is winning the war, the denominator grows a lot bigger than the numerator, so the function is going to be settling on 0. Now, if the numerator is winning the war, there will be no horizontal asymptote. We'll talk more about that in the video for slant asymptotes and holes. But now the numerator is winning the war. Okay, so what's going to happen is I got to be a little bit careful with this argument. You'll see in the video for slant asymptotes and holes. But it's going to kind of look a lot like a 2x piece. So notice that's basically what this is saying is that the numerator is going to be getting way bigger than the denominator. When you have a large number in the top over a not so large number in the bottom, that number is going to be pretty big. It's going to be getting larger. So for this situation, the function isn't going to be settling on a horizontal asymptote. It's going to be going towards infinity or possibly negative infinity. So there'll be no horizontal asymptotes in this situation. If you don't like this argument that I'm making for kind of saying that a polynomial is approximately just the same as its leading term, I'd like to offer you a little bit more thorough of a explanation. The explanation I gave is a little bit hand-wavy. Here's something that's more thorough. Let's say we have something like 3x squared plus, how about 3x, I don't know, let's do 4x cubed minus 5x squared plus 6x plus, 7 all over, let's say we have a 3x cubed plus 7x squared minus 9x plus 1. Okay, here's a better argument. I'm going to do the best trick in the math book. I'm going to cleverly multiply by 1. So the 1 I'm going to multiply by, because I'm trying to understand what this function is doing as x gets really, really big. So here's a nice trick I can use. I'm going to multiply the numerator by 1 over x cubed, and I'm also going to divide the bottom by 1 over x cubed. So I'm really just cleverly multiplying by 1 here. I'm multiplying the top and bottom by the same. Now I'm going to go ahead and distribute in this 1 over x cubed into these parentheses. Okay, and let's see what we're going to get here. Well, I have a 1 over x cubed times a 4x cubed. I'm going to get a 4 minus, well, I'm going to have an x squared divided by an x cubed, so I'm going to get a 5 over x. Plus, I'm going to get a 6. I have an x in the top and x cubed in the bottom, all over an x squared. Plus, then I'll get a 7 over x cubed. All over, I'll do the same thing. I'm going to get a 3 plus a 7 over x minus a 9 over x squared plus a 1 over x cubed when I distribute in that 1 over x cubed. Okay. So I really just wrote this function differently, cleverly multiplying by 1. Now the reason I did this is what I'm curious about is what happens as x gets really, really large, or what happens even if x goes towards negative infinity, either one. Well, what's happening is as we're getting really, really big, look, I have a 5 over x, a 5 over a really, really, really large number, like 5 over 10,000, 5 over a million. This piece is going to be getting closer to 0 as x gets really large, or even if x goes towards negative infinity. Same thing here. All these pieces here are going to be getting closer to 0 as x gets really large from the positive or negative direction. So as x is getting really, really, really large, this function is just approaching 4 minus 0 plus 0 plus 0, 3 plus 0 minus 0 plus 0. We're just going to be getting closer to 4/3. There's a little bit more thorough of an example or of a reasoning. You could always do this type of exercise. Maybe I'll show you one more, but this is a more thorough explanation of why, when the numerator and denominator are tied in the war, you can just think that the horizontal asymptote will be the ratio of the leading coefficients. Let me do one. What if the denominator was winning the war? Let's just put a 3x to the fourth here, for example. But now instead of multiplying by 1 over x cubed, let's multiply by 1 over x to the fourth. Okay, 1 over x to the fourth. Okay? So the trick of what I'm multiplying by is basically I'm looking at all of the terms and I'm looking for what the largest power is. It's an x to the fourth. And I'm multiplying top and bottom by 1 over x to that power. Now when I multiply that in over here, what am I going to get? I'm going to get a 4 over x minus a 5 over x squared. Plus I'm going to get what? A 6 over x cubed plus a 7 over x to the fourth. All over. Well, what am I going to get here? I'm going to get a 3 plus a 7 over x squared minus a 9 over x cubed plus a 1 over x to the fourth. So I just rewrote this a little bit differently. Again, notice that the denominator is winning the war. If we let x get really, really large, or if we let x go towards negative infinity, well, this 4 over x is getting really, really large. It's like I cut a pizza into a million slices and I'm taking 4 of those slices. I got pretty much no pizza. I got no pizza. This is getting closer to 0. That's getting closer to 0. That's getting closer to 0. That's getting closer to 0. This is getting closer to 0. This is getting closer to 0. This is getting closer to 0. So as x is getting really, really large, what is r of x doing? Well, the numerator is getting closer to 0, and the denominator is getting closer to 3, which is just going to end up being 0. It's just going to end up being 0. You know, you cut a pizza into 3 slices, you took none of those slices, you got no pizza. So that's a little bit thorough of an argument about why, when the denominator is winning the war, the function is just going to get sucked down to 0. Again, the way I just think about it is you got a really big number in the bottom, you got a smaller number in the top. That's going to be getting closer to 0. Okay, so I hope this kind of cleared up a little bit of the confusion about end behaviors and horizontal asymptotes when we're talking about rational functions. Okay, we'll see you in the next video. Take care.